Japan's Kansai Airport is sinking seriously. It is an expensive warning the whole world can see. Yet China chose to ignore it in order to pursue a far riskier project. Right in the middle of waters exposed to the strongest storms in the Pacific, they are pouring 14 billion euros into building a solid artificial island. There is no way back. When the mud layer beneath the seabed was too weak to support the terminal, they drove 20,000 steel pipes through the ocean floor to force the ground to stiffen. This is the story of the most daring construction project of the 21st century, where the line between an engineering marvel and a financial disaster is only one storm away. Before laying the first brick, the engineers faced a hard truth. The seabed here is not rock. It is a soft, soupy layer of mud, tens of meters deep, with a very loose structure. Multi-beam sonar surveys scanning the seafloor revealed a massive risk. If rock and fill were dumped directly onto this mud layer, the entire airport would slide and collapse after just one storm. Worse still, beneath the mud are pockets of methane gas and hollow geological cavities. A single exploratory drill in the wrong spot could trigger a gas blowout or severe subsidence. More than 20,000 exploratory boreholes were carried out. The engineers were not just drawing maps, they had to analyze the seabed in detail. They discovered that the sediment layer here is extremely sensitive to vibration. With even a mild earthquake or even resonant shaking from aircraft taking off continuously, the phenomenon of soil liquefaction will occur. Solid ground would turn into liquid almost instantly, destroying the terminal and the runway. The most alarming issue is not what they could see, but the uneven thickness of this sediment layer. In some places, the mud is only 5 meters thick, but a few hundred meters away, it can be as deep as 40 meters. This disparity creates the risk of differential settlement, the biggest threat to any airport. If one part of a runway sinks faster than another by even a few centimeters, the surface can crack severely, causing accidents when aircraft are moving at speeds of 300 kilometers per hour. The challenge, then, is not only to stabilize the ground, but to make it uniformly stiff, absolutely evenly, across an unprecedentedly large area. To fill in 21 square kilometers of sea, an area equivalent to 3,000 FIFA standard soccer fields hauling soil by truck from the mainland was not feasible. It would require billions of cubic meters of material. China used its most optimal solution, the largest dredging fleet in Asia. Leading the effort was Tiankun, the vessel nicknamed the Island Builder. This is not an ordinary ship. It is a mobile seabed extraction system. At the bow is an ultra-durable steel cutterhead with a large diameter, spinning at high speed to crush coral rock and hard seabed rock. A pumping system rated at 6,600 kilowatts then sucks up the mixture of water and rock and shoots it as far as 15 kilometers through a floating pipeline system, or sprays it directly into the air to form gigantic arcs of sand. Tiankun's output reaches 6,000 cubic meters per hour. To make that easier to picture, it can dig an Olympic-sized swimming pool and fill it in under an hour. But Tiankun does not work alone. A supporting fleet of dozens of vessels, self-propelled barges, and GPS positioning ships turned Jinzhou Bay into one of the busiest maritime construction sites in the world. They operated like an automated production line. Cutter ships broke rock, suction dredgers cleared the seabed, and sand-spraying ships filled the gaps. This process was coordinated by a central AI system, ensuring that not a single square meter was left untouched. Operating continuously, 24/7. This fleet pumped hundreds of millions of tons of sand up from the seabed, gradually pushing the sea back. But dumping sand was only the beginning of even greater engineering challenges. The freshly pumped sand is saturated with water. It is loose and weak. If construction began immediately, the airport would sink uncontrollably. This is exactly when Chinese engineers had to look to real-world experience from Japan's Kansai Airport. Kansai was built in the 1990s on a thick layer of clay. Even though the Japanese calculated very carefully, the airport has still subsided by as much as 11 meters, since it opened far beyond every forecast, forcing them to repeatedly raise the seawalls and jack up the terminal's foundations. Kansai's subsidence repair costs became a major financial burden. To avoid repeating that problem, China did not choose the traditional land reclamation approach. They adopted a far more aggressive, multi-stage process of forced ground stabilization. Instead of waiting 20 years for the ground to settle and stabilize on its own, they forced it to stabilize within 2 years. Millions of plastic drainage panels were driven 40 meters deep into the ground like conduits. Then they used vacuum consolidation. Pumps pulled air and water out of the soil through these drains, creating strong negative pressure that squeezed soil particles tightly together. And they did not stop there. To ensure maximum densification, a system of high-energy vibratory rollers was deployed. These machines repeatedly dropped weights of dozens of tons from height onto the ground. The impacts created artificial shock waves, simulating tremors to force sand grains to rearrange into their densest state. Measurements afterward showed an impressive result. The projected residual settlement of Dalian Airport after completion would be under 20 centimeters over 50 years. Compared with the multiple meters seen in similar projects in the 20th century, this represents a major advance in geotechnical engineering. They turned a soft mud layer into an artificial foundation, with mechanical properties as stable as bedrock. Building the artificial island was only the first step. Protecting it from wave impact was another critical challenge. These waters lie along the path of tropical cyclones and harsh winters. Waves here can reach heights of 10 meters, carrying enough energy to break concrete. Moreover, this project was not designed for today, but for the next 100 years, meaning it had to account for sea level rise scenarios driven by climate change. The dike encircling the airport is not a simple wall. It is a multi-layer defense system stretching for dozens of kilometers. The outermost layer consists of special concrete blocks, each weighing up to 25 tons. Their shape is designed to interlock when waves strike, forming a unified mass while still leaving gaps that dissipate wave energy rather than reflecting it back. A distinctive feature of this design is the sponge airport model. Unlike land-based airports that typically seal surfaces with concrete to drain water quickly, the surface of this offshore airport is designed to absorb and temporarily store water in large underground reservoirs. When a major storm makes landfall with record rainfall, instead of allowing water to flood the runway and disrupt operations, the system absorbs the water and then forcibly pumps it out to sea through high-capacity pumping stations. This is the largest active drainage system ever installed for a marine structure. Beneath this protective layer lies ultra-durable geotextile fabric, preventing the fine sand inside the island from being drawn outward by receding flows. The island's entire perimeter was designed to withstand a once-in-100-years storm. Computer simulations ran thousands of tsunami and storm surge scenarios to ensure that even under disaster conditions, the airport remained safe. Once the foundation was complete, infrastructure construction began. There was no room for traditional manual building methods. China applied BIM technology at the highest level, creating a complete digital twin of the entire airport before any real-world construction started. Every fuel pipeline, every electrical cable, every steel beam was modeled in three-dimensional computer simulations to check for clashes and optimize installation. This eliminated 90% of common construction errors and saved hundreds of millions of euros in cost overruns. The airport terminal, a massive structure covering nearly 700,000 square meters, was not built piece by piece on site. Steel and concrete components were manufactured at mainland factories with high precision, then transported offshore on huge barges and assembled like modular blocks. This reduced deviations caused by harsh offshore weather conditions and cut the construction timeline in half. The runway, the most critical part of the airport, was built using flexible concrete technology. Because no matter how thoroughly the ground is treated, minor settlement will still occur over time. The runway is made up of multiple layers of different materials, allowing it to bend slightly without cracking. Fiber optic sensors were embedded beneath every meter of runway, transmitting real-time data to the control center. If any section of runway settles by more than 3 millimeters, the computer system will issue an immediate warning so the maintenance team can intervene. To connect this isolated island to the mainland, a 6-kilometer multimodal transport system was built, including both roadway and rail. The challenge was that the bridge piers also had to sit on similarly weak ground. Engineers had to use extremely large diameter drilled shafts, driven as deep as 70 meters down to the bedrock layer to anchor the bridge, ensuring it would not shift even when ocean currents changed dramatically. However, an offshore airport faces one dangerous and constant damaging agent: sea salt. Salt-laden sea spray is highly corrosive to structures. It rusts steel, degrades concrete, and damages electrical systems. To counter this, all reinforcing steel used in the project is either a special grade of stainless steel or coated with a thick protective layer. The concrete is mixed with next-generation anti-corrosion additives, creating a surface that resists the chemical attack of seawater. But the risks do not come only from nature. An airport in the middle of the sea raises a major rescue and response problem. If an aircraft catches fire on landing, fire engines from the city cannot arrive in time. That is why this airport has a high-standard on-site fire station, along with a fleet of high-speed rescue boats on standby 24/7. They even designed water surface emergency landing zones around the island, where automated equipment can deploy to contain and extinguish fires on the sea surface if jet fuel spills. The power supply and air conditioning system were also specially designed. Because it is isolated offshore, the airport cannot rely entirely on the mainland power grid. An independent power plant, combined with solar energy and a large battery storage system, was built on the island. The airport can operate on its own for 7 consecutive days if all connections to the mainland are completely severed. This is the highest level of energy security standard, typically seen only in critical infrastructure facilities. When the airport is completed, it will be an impressive achievement. With 4 runways and the capacity to serve 70 million passengers per year, it will turn Dalian into a global transportation hub. The economic payoff is clear. It frees up valuable land in the old city, creates hundreds of thousands of jobs, and drives regional economic growth. But to understand why China is willing to invest 14 billion euros, we need to look wider at the world map. This is not just a civilian airport. It is part of a strategy to expand international aviation infrastructure. Dalian's location is a strategic gateway for influence over Northeast Asia, directly connecting to South Korea, Japan, and Russia's Far East. With this airport, China wants to make Dalian a mega air logistics hub that competes head-to-head with Hong Kong and Incheon. China is not alone in this land reclamation trend, but it is leading in scale. Singapore is building the large Terminal 5 on reclaimed land, and Saudi Arabia is developing coastal projects along the Red Sea. However, the speed and construction methods of the Dalian project are setting a new benchmark that is drawing international attention. The ability to mobilize massive resources in a short time has become a competitive advantage for China's construction industry. However, the true costs do not stop at the figure of 14 billion euros. Environmental scientists point out that reclaiming 21 square kilometers of sea has removed habitat for many bottom-dwelling species and altered local ocean currents. Sediment deposition in nearby areas could shift, affecting other ports and natural coastlines. International experts warn that changing currents could erode natural shorelines dozens of kilometers away, creating long-term environmental remediation costs that cannot yet be fully calculated. China says it has built artificial coral reefs and ecological reserves to compensate, but the long-term impacts still need to be monitored. Moreover, the maintenance problem is continuous. Unlike roads or bridges on land, which may require relatively little upkeep for years at a time, an offshore airport demands careful daily monitoring and maintenance. Pumps must keep running, the dikes must be inspected, and the runway must be measured constantly. If the groundwater pumping system stops operating for 48 hours, the water pressure below can begin to affect the foundation structure. Its operating costs will be far higher than those of a typical airport. That is, the price of building in a marine environment. Looking back at the entire project, what do we see? Not just concrete and steel. It is a statement of engineering capability and an ability to expand living space. China has shown that in the 21st century, geography can be altered. If land is scarce, they will create land. If the sea is deep, they will fill the sea. The dredging technology, weak soil treatment methods, and the scale of resource mobilization in this project have set a new standard for global construction. The techniques refined in Jinzhou Bay are now being applied in many other places. From seaports in Africa to land reclamation projects in the Middle East, this artificial island construction technology is becoming increasingly widespread. It is opening a new trend in which people are no longer limited by natural coastlines. Floating cities, undersea data centers, and offshore airports will become inevitable as demand for space continues to grow. 14 billion euros may be an enormous figure for many people, but for an economy that lacks room to expand, it is a necessary investment in the future. This offshore airport is not just a port for airplanes. It is proof that when humans confront limits, creativity and engineering can solve problems. And when the first plane takes off from the middle of the ocean, the world will understand that Earth's map is no longer fixed. It can be redrawn, as long as there are sufficient resources, engineering expertise, and technology to make it happen.